Thanks for joining us in our course on understanding medications. In this lesson, we're going to learn about the general mechanisms by which our medications affect neurotransmissions. And the way in which we're going to approach that is by first reviewing the steps that are involved in neurotransmission, and then by placing the medication's mechanisms in the context of those steps. So very simplistically, when a nerve gets excited or depolarizes, there's an electrical impulse that travels down the neuron to the far end of the neuron, and that's called the end terminal. And at that point, we need to transmit that signal to the next neuron. But most of the neurons, the electrical impulse is not able to just go into the next neuron. What we do in most neurons is that we use a chemical messenger called neurotransmitters. And those chemicals are packed up into secretory vesicles. Vesicles are little balls of the agent, the neurotransmitter. And as the electrical impulse comes down to those vesicles, what that is doing is instructing the vesicles to fuse onto the end terminal, and as it fuses onto the end terminal, the neurotransmitters are going to be released into the synaptic cleft. So now we have a bunch of neurotransmitters in the synaptic cleft. And note that those two neurons here, they're not actually touching. There's an incredibly small distance for diffusion of the neurotransmitters. So the neurotransmitters don't take hardly any time at all, a matter of just a few milliseconds or a few thousandths of a second in order to get from the one cell to the next and latch onto the receptor. When that happens, the effect on this next cell is determined by whether that neurotransmitter that's released is an excitatory neurotransmitter or whether it's an inhibitory neurotransmitter. If it's an excitatory neurotransmitter, it's going to bring that second cell closer to what we call depolarization. And what that means, it's going to be more likely that that electrical impulse is going to start down that second cell. If it's an inhibitory neurotransmitter, it's going to make it less likely that that depolarization will occur. And when you imagine this, you need to keep a number of things in mind. Firstly, we cannot just change the strength of the message to the second neuron. So how is it that we change the impact to the second neuron? Well, the way that we do that is to adjust the frequency of the impulses that go to the second neuron. So we can have it very infrequent, so very infrequent, or very, very frequently. Another thing to remember is that you have to be able to degrade that neurotransmitter almost immediately. You think about it. If you had a peripheral nerve that was going over to the muscles of the hands, and it was instructing the muscles of the hands, the neurotransmitter acetylcholine was instructing the muscles of the hand to contract. If you weren't able to degrade that acetylcholine down really, really quickly, then your muscle in your hand would be constantly contracted. For the respiratory system, you need to be able to relax, and contract. You have to have those degraded really, really quickly. So how are we going to degrade the neurotransmitter down at the synaptic cleft? Two ways. We have an enzyme that's there that's going to be able to degrade that very quickly, and then a second mechanism is that we have a reuptake kind of pump that pumps it back into the neurotransmitters. It pumps the neurotransmitters back into the first neuron. And all of that happens within a few milliseconds. So now that we've taken that and we've got a picture of that in our mind, let's take a look at the drugs, the general mechanisms by which our drugs act. Well, there's a number of ways. The first one is an antagonist. We can actually take a drug that binds to that receptor on the second neuron and prevents the neurotransmitters to bind onto that receptor. That's an antagonist. A second way is to have an agonist. It would bind to that same receptor and it would cause the same physiological response as the natural neurotransmitter would. Another way is to have that enzyme affect that enzyme that's in that synaptic cleft. And the way we would do that is we would inhibit that enzyme. If we inhibited that enzyme that actually breaks down the neurotransmitter, we would end up with the neurotransmitter being in the synaptic cleft longer. And then another thing that winds up in the neurotransmitter being in the synaptic cleft longer is to affect the reuptake pump. Remember that pump that kind of pulls the neurotransmitters back into the original cell. Okay, so now what we're going to do is take a few examples of that in the next couple lessons, and I'll see you in the next lesson.